So good morning, everyone.
Good morning.
So we stopped at we finished the TM or E modes in a rectangular waveguides, and we were to continue with the TE or H modes. And in this case, what we said is that the H modes have Hz being a solution of the Helmholtz equation, that is in a dielectric free point, a source free point on the dielectric inside the waveguide. And the E field will be everywhere transverse to the direction of propagation, the propagation axis. Now, we need to have that the tangential components of the electric field must vanish at the walls, because we have been assuming that our walls are perfectly conducting surfaces. And therefore, what that means is that since E is related to the derivative, the special derivative of H of Z for the TE modes, then we must have that dHz dx be equal to 0 at both x equal to 0 and x equal to a, which means that EY is going to be 0 at those two points. And dHz dy must be equal to 0 at both y equal to 0 and b, so that Ex vanishes at both y equal to 0 and b, and y equal to b. So the solution of the homogeneous Helmholtz equation is then readily going to be seen that it has to be a cosine function, so that when we differentiate it with respect to x and y, we get the signs that will make the E field vanish. And therefore, Hz must be given by HMN cos of m pi by ax cos n pi by by, where m pi by a is kx, that is the separation variable in the x direction, and n pi by b is ky, separation constant in the y direction. And m can go from 0, 1, 2, up to infinity. N can be 0, 1, 2 to infinity. But there's one thing we have to notice, is that if m is equal to 0, n cannot be equal to 0, and vice versa. That is, m and n cannot be 0 at the same time for this to be a valid solution for the propagation of TE modes inside our waveguide, we shall see why. If m and n are simultaneously 0, then we can see that the cosine of m pi by ax, cos n pi by by are going to be unity, both of them, and h of z is going to be a constant, and therefore when we differentiate it with respect to x or y, it will vanish, and therefore there will be no electric field. So the tangential component, or the tangential field components for the propagating modes, are then going to be given by the ET given by j omega mu by kc squared, z cross gradient of hz, and this gives us an x component, which I seem to have left out the direction unit vector, and the y component. And the ht is given by that value, that is j beta by kc squared, where I'm replacing the gamma with the j beta because we are dealing with propagating modes where the alpha is going to be equal to 0. And this is therefore j beta divided by kc squared and multiplied by the gradient of hz. And we get a positive, or that is our next component and a y component as well. So for a rectangular section guide with A greater than B, the mode with the lowest cutoff frequency is then going to be given by TE10 mode when M is equal to 1 and N is equal to 0. I guess yesterday I did ask you guys to make a table in which we were relating the cutoff frequencies of FC by 2A, okay? That is in terms of FC by 2A in a guide that had A approximately equal to twice B. I don't know whether you have done that already. So we can see that for the TE10 mode, the fundamental or the cutoff frequency for that mode is going to be just equal to C by 2A, where A is the width of the guide, and therefore the cutoff wavelength is just twice the guide wavelength. And therefore we see that the first value we get there is a sine wave, that is half a sine cycle, and then we can get the second sine cycles and so forth. So the TE10 mode is hence the dominant TE mode in a rectangular waveguide. The TE10 mode is especially important to engineering because if you looked at its distribution, the field distribution, we shall see that it will have the lowest attenuation of all propagating modes because the E field will only be in one direction, that is in the y direction. So it appears to be a polarized, a plane polarized, a y polarized plane wave traveling within the waveguide. It's not a uniform wave because the E field is not uniform over the distance, okay, over the width of the guide, but varies as a sine. So it has an E polarized and polarized in only one direction, just like in the case of the TEM propagation. And therefore we look at the first example for this particular case, and we are required to write the instantaneous expressions for the TE10 mode. Hence, we sketch the electric and magnetic field lines in a typical XY, YZ, and XZ planes, and then proceed to sketch the surface currents on the guide walls. So the first thing we have is that we use the solutions that we have already obtained, multiply those solutions with the exponent of j omega t, and remembering that we had a beta z as well, and we take the real part thereof. And once we do that, we'll get that hz of xy is going to be given by h10, the cosine of pi by ax, multiplied by the cosine of omega t minus beta z. And we have only one transverse component, the y component is equal to 0, and therefore we have a minus beta by kc squared pi by a h10 sine pi by ax sine omega t minus beta z. So what we can do is that if we look at this kc squared, we can always see that this is the kc squared, which is the same as pi by a, and therefore we just have beta by kc, or a by pi. So for the x component of for the E field, we have the x component of the E field is going to be equal to 0, and we have only the EY, and we have that value there. And this can be, again, as I said, this is just omega mu a by pi h10 sine pi by a x sine omega t, where the beta is again given by the usual connotation that we have, that is a dispersive kind of propagation. So we now notice that we have only EY, HX, and HZ that are non-zero, and EY and HX are independent of the Y dimension. So at x equal to a by 2, that is in the middle of the guide face cross section, then sine pi x by a is going to be given by unity, and the cosine of pi x by a is going to be equal to 0, and therefore only EY and HZ will be varying sinusoidally with Z along that plane and are non-zero. And hence, at a time t equal to 0, the electric and magnetic field lines in the xy plane are then of that nature. That is, the E field is facing in the y direction and the H field is horizontal. And therefore, if we can have two guides or two ways of applying the guide in practice. When we have it in this horizontal form, any components that will be connected with the guide lying flat like this will be called the H-plane kind of circuits. And if we are having it in the components are connected to the height, okay, in the height direction, we'll call that the E-plane. And if we look at that, we are seeing it in the beta Z or the YZ plane. They look in that, or they look like that. And then this would be the XZ plane. That is, we are looking at the top, okay, at the top of the plate of the guide, and that's how the guide will be looking, or the fields will be looking like this. So in the XZ plane, all the field components are non-zero, and the slope of the H and Y and E lines are governed by dx dz of H equal to beta by k c squared pi by a tangent of pi by ax tan beta z. And thus, the field lines are independent of Y, and the surface current density on the guide walls is going to be related to H by Js equal to the N cross H. That is the discontinuity condition on a perfectly conducting surface. And N is, of course, the outward normal from the walls, where the outward normal on the walls, of course, are pointing into the guide at each corresponding wall. So hence, at t equal to 0, we can have that Js at x equal to 0 is going to be given by the minus of y, hz, 0, yz, and 0, and we get a value of h10, the cosine of beta z, the negative. And Js equal to x equal to a, we apply that and put this value there. So we'll put cos beta z there, and we get a value of J of s at x equal to 0. That is the same as the value of the x equal to 0 equation there. The reason why we have that x equal to 0 is because we'll put a cosine of pi, and the cosine of pi is going to be negative. So there should be a value, okay? So that's what the value is going to be. This one is just going to be the same as that because of the negative nature of that cosine. So there's a negative number missing here because we'll be multiplying that one by the cosine of pi. And Js equal to y equal to 0 will have two components, that is the f component and the z component, and we get a value of the minus of Js equal to x equal to 0, and the Js equal to that value there. Now, this one is not correct. This is a bit, this is not correct here. So this will have to go out. I'll correct this for you. Because when we put the value of beta z, okay, the hy, that does not come in, so to speak. So the surface currents on the guide walls for the TE10 mode in a rectangular waveguide will then be as shown there. That is, we'll have the current moving. They are moving up the side walls, going to a common point, and then going back into the other the other surface. So it's going around the guide walls, so to speak. So example 3, a standard air-filled waveguide have been designed for the radar bands, with one type designated the WG16 being suitable for the X-band applications and has dimensions of A equal to 2.29 centimeters and B equal to 2.02 centimeters. If it is desired that the WG16 guide be operated only in the dominant mode, this is called single mode operation, and the operating frequency be at least 25% above the cutoff frequency of this mode, but no higher than 95% of the next higher cutoff frequency, what is the allowable operating frequency range? If you have already made up the table I asked you guys to make yesterday, you would recognize that in a rectangular waveguide, the next higher mode will be a TE20 mode rather than a TE01 mode. That is when A is greater than B. It will be the 20 mode that will be propagating next when the frequency is raised. Okay, so this is the way you'll be designing waveguides for your application. So we are giving it a 95% so that if there are any discontinuities or issues with our guide, that the cutoff frequency of the next higher mode does not drop down, that causes the cutoff frequency of the next higher mode becomes lower, we won't be affected. Okay, so the bandwidth is just between the 25% above the cutoff frequency of the first mode and 5% below the cutoff frequency of the other. So this is what we do. First of all, we determine what the cutoff frequency is going to be for the fundamental mode, and we saw that was going to be given by C by 2A because we are using a hollow waveguide. Otherwise, we'd be dividing this by the square root of the relative permittivity multiplied by the relative permeability of the dielectric inside the guide. But since it's air, we are just going to use the C by 2A, and we get a value of 6.55 gigahertz. Now, you can notice I've given the value of the velocity of light in terms of frequency and centimeters. We know that the hertz is simply 1 over a second, and therefore the 3.0 times 10 raised to 8 meters per second can be converted into meters and centimeters per second, and then the per second we can take that one and make it gigahertz, because we'll see that 3.0 times 10 raised to 8 meters per second is the same as 30 times 10 raised to 9 centimeters per second, and the 10 raised to 9 is a gigahertz. Okay, the 10 raised to 9 per second is a gigahertz, so we are putting it as gigahertz centimeter. The guide walls or the guide dimensions are given in centimeters, and that's why I'm using centimeters here. If it was meters, I would use meters rather than the centimeters. And this makes it easy for us to compute quickly frequencies and dimensions when we are dealing with microwave or microwave signals. So that, for our guide, the cutoff frequency of the first fundamental mode or the dominant mode is 6.55 gigahertz, and the second or the next higher mode that will be propagating will have a cutoff frequency of FC20, and that will be given by the value of C by A, and we get a value of 13.10 gigahertz. And thus, the range for which we require to operate the guide will be 1.25. We were told that it should be 25% above the cutoff frequency of the dominant mode, therefore 1.25 FC of 10, and about 95% of the next higher mode. And therefore we have a frequency range of 8.19 gigahertz to 12.45 gigahertz, which is the X-band mode, the X-band band of the electromagnetic spectrum. So for a propagating TEMN mode, the power at the rate or the rate of energy flow in the positive Z direction will be obtained from the time average Poynting vector as follows. Pmn is going to be given by a half the real part of the integral of the Poynting vector, the time average Poynting vector. Of course, this one should usually be put inside here in the integral, but I've just left it outside because integrating the real part is the same as taking the real part of the whole integral. And therefore, we get a value that is going to be given by a half the real part of the wave impedance for ZTE modes, and taking the integral of the hy and hx squared dx and dy. That is, we are integrating over the cross section of the guide. And now, if we look at this integral here, we'll have the sine m pi by a and cosine n pi by b everywhere, and we'll get a value that whenever m is not equal to 0 and n is not equal to 0, we'll get a value of ab divided by 4. And when it's equal to m or n is equal to 0, we have a value of ab divided by 2. And thus, Pm nz will be given by that value multiplied by the epsilon naught of m, epsilon naught of n, and we shall divided by a by b, where the epsilon naught are related to that value there. And it will be multiplied by that kc squared that we've been dealing with. So E0m or epsilon 0n are called the Neumann factors, and they are given by epsilon 0m is 1 when m is equal to 0, and it's equal to 2 when m is greater than 0. And epsilon naught is n is going to be equal to 1 when n is 0, 2 when n is greater than 0. So because of the orthogonality of the eigenfunctions, the total power when two modes TE, Mn, and TE, PQ, where Mn and PQ are integers, are simultaneously present, it will be the sum of the powers in each of the modes. That is, we can have it that the total power P is going to be given by Pmn plus PPQ. And hence, and since we have seen that the integral over the width of the guide of the sine m pi by ax and sine p pi by ax dx is going to be equal to 0 whenever p and m are not equal. So for low loss waveguide, the power orthogonality will still be valid, except for the case when two or more degenerate modes, whereby degenerate modes, just like we say degenerate energy levels in physics, in the physical electronics, we also have degenerate modes where they have the same cutoff frequency, although they have different mode indices. So when two or more degenerate modes are present, because the presence of load losses may result in a strong coupling between the degenerate modes. So what are the discontinuities? We'll get discontinuities in the waveguide. We've been dealing with a uniform section, cross-section waveguide. But in some cases, we'll find that that one is boring, and especially in terms of application. Even in plumbing, we have to put gates sometimes. We have to reduce the diameters of the pipes in some places to try and increase the pressure and so forth on the speed. So we can introduce shunt capacitor susceptances into the waveguide in the form of metal diaphragms with an iris as shown below. That is, we could, in the H-plane, we can add an iris, which is a metal blade inside the guide that reduces the cross-section or the height of the guide at that particular section. And this will form a capacitance because by introducing this value here, it's like we have reduced the gap width, and therefore, since the electric field is meant to be, is proportional to, inversely proportional to the distance between the plates, then the electric field is increased. And the increase in the intensity of the electric field is a capacitive effect. We could put it in the E-plane, that is, the blades could be put in the E-plane, and therefore we are reducing the we are reducing the width of that waveguide. And this, we have introduced new paths for the current to flow, and therefore we are increasing the current. And because the magnetic field intensity is related to the current, then it means that that is an inductive effect, and we therefore have an inductive iris. Another thing we can do is that we can choose a point on the face of the guide, and we put in a conducting post, or we can use a screw, just like shown there, which we can vary the distance. The distance, of course, varies the height of the guide at the position of the screw itself. Usually we'll try to put the screw or the post along the middle of the broad face, because that's where the electric field for the TE10 mode will be highest, and therefore it will be most sensitive, rather than putting nearer to the other walls. Okay, and therefore that's why we have that kind of thing. And if it's a screw, since we can change the value of D, we can call it a tuning post or a tuning screw. So the fields must satisfy, whenever we have these discontinuities, the fields must satisfy further boundary conditions on the metal surface with an iris. If the waveguide is in the TE10 mode of operation, the additional boundary conditions then will require that we consider all the higher order modes referred to as the cutoff modes in our case. That is, all the higher order modes will have cutoff frequencies above the fundamental or the dominant cutoff frequency of the guide, which is the design whatever frequency, and therefore they may not be propagated, and we shall see that they quickly die off far away or a short distance away from the discontinuity. So the guide, being designed such that only the dominant mode propagates, the cutoff modes will be localized near that iris. So for a capacitive iris, the E lines are in the Y direction, and the reduction of B to the gap with D can be expected to enhance this field, as well as the stored energy in the local electric field. And thus, we can have as acceptors a capacitive susceptance BC, which is normalized to ZTE, which is equal to BC ZTE 10 mode, and equal to 4B by lambda G natural log of 1 over sine pi D by 2B. This is from a detailed analysis, not from a simple thing we have just shown. The detail is not important for us now. So this expression is accurate up to 5% over the normal range of operation of that guide. And we have seen the normal range of operation of the guide will be from the cutoff frequency to the cutoff frequency of the next higher mode. The inductive iris provides additional current paths in the Y direction, and therefore it causes new longitudinal H fields along the iris opening. The energy stored in the local magnetic field will therefore be increased, and we then have an inductive susceptance normalized to the waveguide or the wave impedance, and this will be given by the minus of lambda G by A and the cotangent squared of pi D divided by twice pi. So another discontinuity that provides shunt susceptance is a conducting post, like we have shown in the diagram, that protrudes into the guide. If D is small, the susceptance is going to be capacitive. That is, if we have only a short protrusion, but when the D is made larger compared to the height of the guide, okay, we'll see that considerable current will flow along the post, and this will give rise to an inductive effect. And resonance will occur at a value of D close to 3/4 of B, and for D longer than this, the susceptance now becomes inductive, just like when we were dealing with resonators. So in practice, the post is usually in the form of a screw, which is installed in an axial slit in the center of the broad face, where the H is, or the magnetic field intensity is a minimum and does not therefore disturb the field pattern significantly. So by adjusting D and the position along the guide, the impedance matching that is similar to that of stub matching that you studied in the third year treatment of ECT or tuning can be provided. So, example 4. Measurements on a WG10 S-band waveguide, that is with A equal to 7.21 centimeter and B equal to 3.40 centimeter, feeding a horn antenna, show a VSWR, or a voltage standing wave ratio of 2.0 at the operating frequency of 3 gigahertz and existence of an electric field maximum 12 centimeters from the neck of the horn. Find the location and dimensions of a symmetrical inductive iris necessary to achieve a perfect match. And we assume that the guide is lossless. So again, the dominant mode cutoff frequency is computed, and we show it to be 2.08 gigahertz. The guide wavelength is given by the guide or the wavelength in free space or in free medium divided by the frequency correction factor or dispersion. We get a value of 13.9 centimeters. The measured electric field is maximum is located at 12 centimeters over 13.9 centimeters, and we can get this as, this is the guide, whatever the level of the guides, okay, guide wavelength, that is about 0.863 guide multiplied by the guide wavelength. And therefore, when you deal it with this way, we can now use the Smith chart to try and get the values that we are being asked to get. So it's that from the neck of the horn. And at this location, the normalized effective load resistance is going to be given by RL equals to RL by Z naught, which is equal to S, the standing wave ratio, and hence we can get the conductance for the load, which is YL by the Y naught, that is the normalized conductance, and we get a value of 1 by S, 0.5. And then we can proceed with the application of the Smith chart to obtain a value for D of about 4.72 centimeters, gated at about 0.863 minus 0.348 of lambda G, which is about 7.16 centimeters. So the transmission line analogy of waveguide propagation, which we already have looked at, may be applied to many discontinuity problems as illustrated below. That is, when we have an iris, we can always have the position of the iris can be represented by a lumped capacitor, okay, for that capacitive iris, a lumped capacitor to take care of the discontinuity, and then the rest of the waveguide will proceed. That is, these are sections of the waveguide with a characteristic impedance Z naught, which we showed already can be obtained in terms of ZTE or ZTM and so forth. And Z naught will be, okay, on the other side of the discontinuity. Now, if we have an iris parallel to the E, then we can introduce an inductance rather than a capacitance, and again we have the same thing. So part of this can be given as shown. We could have a guide section that has a narrow guide section with a small height B, okay, but then it's connected to another section of guide with a larger B. So we have a step change in the height of the guide. So this is called the H-plane changes. And therefore this can be modeled as follows. That is, we can have a guide with a characteristic impedance Z01 and propagation constant gamma 1 connected to another one which has a characteristic impedance Z02 and a propagation constant gamma 2. And then because of the discontinuity, we apply a capacitance there, because we can see that this is exactly the same as that when we look at it from this end. That is, if we were to look at it from that end, we'll see that blade appearing there. So we recall that in an iris, an iris in a waveguide will behave like a shunt reactance on the equivalent line. And the reactance will be inductive when the edges of the iris are parallel to the electric field, and capacitive when the edges are normal to that field. So an abrupt change in dimensions is represented by a junction between two transmission lines of different characteristic impedances with an appropriate shunt reactance connected at the junction as we have shown. So the determination of the actual value of the shunt reactance is actually supposed to be obtained from a field problem solution. And this can be solved through matching the solutions at the junction, just like we were matching the wave functions at the barriers in the physical electronics. So the field at the discontinuity, as represented by the sum of the dominant mode and the higher order modes with relative amplitudes determined from the matching and of the tangential components of the electric and magnetic fields at the discontinuity. We know that the tangential components of the electric field must be continuous across the boundary, while the fields and the magnetic field as well can be done like that. But when we have normal or real perfectly conducting surfaces, we know that the magnetic field is going to be discontinuous, the electric field will vanish. So while the higher modes are required by the boundary conditions, this will decay rapidly away from the discontinuity region because of their cutoff frequencies being generally much higher than the operating frequency, since the guide will be operating at its design, and it's designed only for single mode operation. So the load and the generator terminations will be, when we are applying this, will be assumed to be sufficiently far away from the discontinuity so that they are not affected by the fields of the higher order modes. That is, by the time the fields from the higher order modes arrive at the load or the generator, they would already have been attenuated to zero. And this is the reason why transmission line analogy will apply. That is, the effect of the discontinuity of the dominant mode will suffice. So the higher mode or the higher order modes do not contribute significantly to the voltage at the discontinuity, but their contribution to the current will be substantial. And although the current is continuous across the discontinuity, as it will be required by the boundary conditions, the current associated with the dominant mode will be discontinuous by the same amount contributed by the higher order modes, because this will not be propagating beyond the discontinuity. And this is what will be accounted for by the shunt reactance that we have connected across the discontinuity. So now there is one thing we have talked about, the wave impedance, and you have seen that the wave impedance of a waveguide depends on the mode of propagation. That is the mode of operation, that is either TE propagation or TM propagation. And now we have seen that in transmission line theory, there is a very important concept that is very beneficial in terms of analysis and design, and this we call the characteristic impedance of that particular guide, transmission line. And now we are going to try and look at, can we actually define a similar a similar kind of quantity for waveguides, which will become useful to us in the design analysis of microwave or waveguide circuits. And this turns out to be okay, but one thing we can see is that if you looked at the cross-section of the waveguide, say for example carrying a TE10 mode, the electric field will be maximum at the center of the broad side of the guide, and then it will diminish towards zero at the guide walls. Okay, and therefore it's an ununiform plane wave. As far as we are concerned in our case, the E field is not constant as it would be in an actual two-conductor transmission line. But the voltage between the top plate and the bottom plate is to be given by the line integral along a line of electric field flux. And therefore, the voltage between the top and the bottom plates of the guide will be different depending on which line we choose to integrate from. So we can always decide that we are going to integrate them along the line that where the electric field is maximum, and we'll get a value of the voltage. Then the current itself also has a, it has a sinusoidal kind of function, because the H field that we'll be using to integrate to get the current is also non-uniform, and therefore we can always define what the current will be, and then we divide the voltage we have obtained divided by the current, and we'll get an impedance which we can choose to call a characteristic impedance. And this is what we are going to do now. So for a transmission line operated in the TEM mode, the characteristic impedance is a unique value, and they will be defined as Z0 equal to the ratio of the voltage amplitude and the current amplitude of the forward propagating wave component, or the minus of the voltage amplitude and the current amplitude of the negative or reflected voltage and current waves on that line. This is what we saw. The voltage between the conductors of the line is also unique, because it will be defined as the integral or the negative of the minus integral over the path of electric field, okay, line, okay, between from one conductor to the other conductor. In a waveguide with a single conductor, the value of the integral will be path dependent. Depends on which path we choose to integrate from. So in a rectangular section waveguide, which is operated in the TE10 mode, we have that Hz is equal to H10 cosine of pi A by X multiplied by X. And therefore, the transverse magnetic field is just going to be given by J beta by Kc H10 sine pi by AX, which gives us a value of minus X cap J lambda C by lambda G, where we have used the value of beta and Kc, divide them to get the lambda C by lambda G, that is the cutoff wavelength, divided by the guide wavelength, multiplied by H10, the sine of pi by AX there. And the transverse electric field is given by the J omega mu by Kc, H10 of the sine pi by AX, and we get a value of minus J ZTE lambda C by lambda G and H10 sine pi by AX, where ZTE is of course the wave impedance for the TE modes. So for the TE10 mode, we see that the electric field, or the transverse electric field, is maximum in the plane x equal to A by 2. And thus, we may define our value of the voltage as the integral from the bottom plate to the top plate along that path, or in that plane of x equal to A by 2. And we get a value of ZTE lambda C by lambda G H10 integral from 0 to pi to B of sine pi by AX dy, okay, X and dy, and we get a value of ZTE lambda C by lambda G and multiplied by B H10 there. On the guide walls, we have that the N cross H is equal to the surface current density, and therefore in the axial direction, that is in the Z direction, we can write that Z cap of JZ is going to be given by N cap cross HT, that is the transverse magnetic field. And therefore at Y equal to 0, we can always get the value of that electric field or the current density or surface current density in the Z direction, and we get a value of lambda C by lambda G H10 sine pi by AX. And therefore the total current in that direction, that is the total axial current, will be the integral over the width of the plate, okay, and the 0 to A of that value, and we get a value of 2A by pi J lambda C pi lambda G H10. And therefore the time average power transported by the wave down the guide will be given by that value P of Z, which is equal to the integral of the Poynting's vector, okay, time average Poynting's vector over the cross section of the guide, and we get a value of that, okay. So the quantities then suggest several ways in which a characteristic impedance of the guide could be defined. One, we may define a voltage current characteristic impedance, which we are going to call Z0, defined as the maximum voltage, that is the voltage we computed along the line of maximum electric field, divided by the total axial current, which is IZ. And we get a value of pi by 2 ZTE multiplied by the ratio of the guide height to guide whatever width, which is called the aspect ratio of the guide. And once we put in the values of ZTE in, we get a value of pi by 2 eta naught B by A multiplied by the root of the ratio between the magnetic relative permeability by the relative permittivity, and 1 by that. So for air guides, that is for hollow wave guides, this will of course be unity and will be dropped, and we get a value of 592.2 B by A, and the square of that, and divided by the guide wavelength divided by the ratio of the guide wavelength to the free medium wavelength, and that will be given in ohms. 2, we can use the power and current relations to define our characteristic impedance. That is, we know that power is usually given by I squared multiplied by the impedance. Z0 is of course a real value, so we are using a half I squared multiplied by R squared, since the I squared is assumed to be a phasor form. So it's I Z dot IZ star. So therefore, we have to take the half, and therefore we get a value of pi by squared by 8 eta naught B by that, and we see this is exactly the same as what we had in this particular case here, okay? And therefore, if we put the values for eta naught, we get about a value of 465.1 B by A root of that lambda G. Now, another variation is a power voltage characteristic impedance, where we are using, instead of the current, we use the voltage. And therefore, again, we get Z0 given by Vm squared by 2Pz, and we get a value of 754 B by A and root mu R by epsilon R of lambda G by lambda ohms. And finally, we can modify the power voltage ratio characteristic impedance, where we are now using a V, where V now is no longer the amplitude Vm, but a root mean square voltage, which we have defined as an, as an equivalent root mean square voltage, okay, averaged over the guide width as shown there. That is, V is defined as the square root of 1 by A integral from 0 to A of Vm sine pi by A x squared dx. And we get a value of Vm by root 2. And once we put this in there, we get a value of 377 B by A root mu R by the epsilon R by G by lambda. Okay, so those are 3 or 4 ways in which we can define the characteristic impedance, and it's up to you to choose one and stick with one. You cannot mix them. So any of the definitions may be applied as long as it is used consistently throughout the analysis, throughout design process. Now, sometimes we'll find that while we are starting with hollow waveguides, sometimes because of matching requirements or changing the phase or shifting phase of the signals, we may be required to fill in the guide. And many times the guide will be partially loaded. Rather than filling the guide completely with dielectric, we just put a dielectric that just fills just part of the guide cross section. So we consider a partially loaded waveguide with a cross section shown below. That is, we have a guide of width A, but along the E plane, we place a dielectric of dielectric constant, or dielectric permittivity, or the electric permittivity epsilon, and here the rest is going to be hollow. So this is called a partially filled guide, and the thickness of the dielectric is T. Since the waveguide geometry is uniform in the y direction, and n is equal to 0 for all Tmn n equal to 0 modes, that is Tm0 modes, then these modes will have no y dependence. And thus, the Helmholtz equation will be satisfied by the axiomagnetic field component is going to be given by d2x squared plus d2y squared of kc h of z equal to 0, with kc given by gamma squared plus omega squared mu epsilon, and can be written separately for the electric and guide regions as, that is, this one is unfortunate. There's no variation in the y direction, therefore this is going to be everywhere 0, so it doesn't matter, it should remove it. So we just have a value that inside the dielectric, the Helmholtz equation that Hz satisfied would be given by d2 dx squared plus kd squared Hz for the region 0 between 0 and t. And in the air section, we have a value kc will be given a symbol ka, so we have a Hz and 0, t, and between t and a. So the kd and ka are the cutoff wave numbers for the dielectric and air regions respectively. So for the propagating modes, the propagation constant for the propagating modes is going to be given by gamma equal to j beta, and must be the same in both the air and dielectric regions. And this will ensure that the propagating signal has phase matching along the dielectric air interface at x equal to t. And thus, the dispersion relations will have the following form: that beta squared, that is gamma squared, equal to k squared minus kc squared, like we showed before. Then in the dielectric region, beta squared must be equal to omega squared mu epsilon minus kd squared. And in the air region, we must have beta squared equal to omega squared mu naught epsilon naught minus ka squared. And the solution for Hz is then going to be of the form: in the dielectric region, it will have a form of A cosine of k dx plus B sine k dx. And in the dielectric, or in the air region, it will have C cosine of ka, A minus x plus d sine ka a minus x. So for the TE and M0 modes, the EZ is equal to 0 and HY must be 0 as well, since the d dy is all going to be equal to 0. And hence, EY is just going to be given by that relation there. And we see that it's going to have two values. That is J omega mu by KD minus A sine K dx plus B cos K dx in the dielectric region. And in the air region, it should have a value of J omega mu by Ka C sine Ka A minus x minus D cos Ka A minus x in that region. So since EY is equal to 0 at x equal to 0, where we have a perfectly conducting surface, and at A, that is the far end wall, then we must have that B and D must all be equal to 0, and the continuity of EY and HX at x equal to t will then yield the following equations, that the minus of A by KD sine K dt minus C by Ka sine Ka A in minus t is equal to 0, and A cos K dt minus C cos Ka A minus t equal to 0. Remember, t is not time, but it's the thickness of our dielectric. And therefore, these two equations can be solved for A and C, and for them to have an untrivial solution for those constants A and C, then we must require that the determinant of the 2 by 2 matrix formed by these two equations must vanish. Okay? And therefore, we must have that Ka, the tangent of K dt plus Kd, the tangent of Ka, A minus t must be equal to 0. And together with the dispersion relations that we already found, that is the relationship between beta and Kd and Ka, then this will be solved either graphically or otherwise for beta, Kd, and Ka at the given operating frequency. That is, this form transcendental equations. Okay, all we have to do is to multiply this one by the dielectric thickness T. Okay, we multiply through by the dielectric thickness T, and for the beta, the beta values, we multiply it by T squared, and then we'll get a value, and then plot those ones between the same whatever axis. We shall see this when we look at the dielectric waveguide later in the course. So sometimes the problem may be only trying to get the cutoff frequencies of a given guide, and therefore, or a given structure. And usually, we don't want to have to go into solving Maxwell's equation or the Helmholtz equation all through just to get just a simple value of the Kc. So there's approximate, or there are simple techniques that have been done or formulated for this kind of work, and this is called the transverse resonance technique for the waveguide analysis. So a propagating mode in a uniform waveguide structure has a propagation constant with the form beta equal to the square root of k squared minus kc squared. And this, if we replace this kc squared by its separation value, whatever constant kx and ky, we'll have it as omega squared, mu epsilon minus kx squared minus ky squared. So when only the propagation constant of the waveguide is of interest, when solving the relevant wave equation to determine Kc is not really necessary. And the field distributions in the guide at cutoff will have a standing wave pattern in the transverse plane, which is equivalent to a transmission line circuit that is in resonance. It's more like when we were looking at a wave impinging on a planar boundary and therefore forming a standing wave. with the reflected waves. So on a resonant transmission line, the sum of the input impedances at any point on that line looking toward the generator and looking toward the load must always be equal to 0. That is, if we were to look at the line, that is at a given point on the line, we turn around and look at towards the generator, we'll get a value of input impedance Zin at that point, and if we look toward the load, we'll get a value of Zin of L there. And this, when we add them together, they must always be equal to 0. So this will be at X on the resonant line looking toward the generator and the load respectively. So this, I think this one I need to, this was a problem there with the Y, I think that's the X. This is the transverse resonant technique, which yields the information on only the cutoff frequency of the waveguide for the given mode. So as an example, let's look at TM modes on a conducting parallel plate transmission line. So here we have the transmission line, and we are saying that it's of width A, and it's extending towards the other direction. So this is in the Y direction. So all we are going to do is to get a value of Y, and we put a line there. Then we look towards the generator. Okay, that is, we have put a shorting plate here. And so we are looking towards the generator and we are looking towards the load on that end. So at cutoff, K is equal to omega root mu pi, mu epsilon equal to Kc, and no propagation down the guide will occur. And the field hence forms a standing wave pattern along the Y dimension. So the equivalent circuit of this operation is a transmission line of length B that is short-circuited at both ends by the conducting plates at Y equal to 0 and B, and having a propagation constant of Ky. So due to the uniform geometry in the X direction, Kx is equal to 0, and the characteristic impedance of the equivalent line is the wave impedance seen by the TM mode having beta equal to Ky, that is, Z dot is equal to Ztm equal to eta Ky by K, where eta is just the square root of mu by epsilon, and K is of course the usual omega root mu epsilon, or omega by C. And at any point between the two plates, we have the Z in looking towards the generator is going to be given by J Ztm tan Ky B minus Y, and looking towards the load, we'll have Ztm tangent of Ky of Y. And thus, J Ztm tan Ky B minus Y plus tan Ky of Y is equal to 0, or in other words, J Ztm equal to sin Ky B over cos Ky B minus Y cos Ky of Y, and we can see that Kc is going to be equal to Ky, which is equal to n pi by B, or n equal to 0, 1, 2, and so forth. And we have solved that problem. So for the partially loaded rectangular waveguide, the situation for the TE0N modes can be represented as shown there. That is, again, we have our guide length here, and this is the distance we are talking about. Then we look towards the generator or towards the load. And in the region 0 less than Y to T, we have beta equals to Ky of D, and we can have a value of Z naught for the dielectric equal to eta K by Ky of D, which is eta by that. And where K naught is omega root mu naught epsilon naught, and n naught, eta naught is mu naught by epsilon naught root, which is the intrinsic impedance of free space. In the region in the air, we have beta is equal to Ky of air, and then Z naught A is just going to be given by that value there. And thus, when we add them again as before, we get a value for, and together with the conditions or the phase matching condition obtained from the phase dispersion relations, we get a value, the solutions of ky of A and ky of D. Now, the mode properties of the rectangular waveguides are as follows. We have an HZ. For TE modes, it has been given the solutions will have that form, which we have included also the propagation in the Z direction. For TM modes, we don't have an HZ. HX is going to be given by those values, and the impedance is, of course, ZTM here. And for, for HY, we have that value, and we have that value of EX. And EZ is equal to 0, ZTE is equal to that value, and ZTEMN is equal to that, and the other one will have the ZTMs as well on the other end. So the TE modes as well, we have ZTM and ZTN. We have their relationship as that. This one will have beta mn by k naught multiplied by z naught. Here kc, the cutoff frequencies are the same for both. The waveguide or the cutoff frequencies, the wavelengths are the same, and the beta phase propagation constants are also the same for both, all of them. So the attenuation coefficient for the non-degenerate modes, we shall see when we look at the attenuation in waveguides or losses. This will be able to derive this expression. So we are going to say that Rm is, of course, the value of Rm corrected to the guide values. And for the Tm modes, the attenuation constant Atm is given by that value there, with Rn equal to omega mu naught by sigma n by twice sigma, which is the resistance per square that we obtained before, and the epsilon naught 0m is 1 for m equal to 0, and 2 for m greater than 1. And I have that value there. So another thing we can get is that we have used a waveguide that has, we are using, it's infinitely long, or it has a very long, it's very long in the Z direction. Now, in some cases, we may cut off that section and we put a short circuit at the end, or we just leave it open. And therefore, we have a section of waveguide, and this will form a resonant cavity. So only ordinary lumped elements such as resistors, inductors, and capacitors, as we have seen, are very difficult to realize above the UHF frequencies, which are above 300 megahertz or 0.3 gigahertz. And this is because the circuits will have the same order of magnitude as these signal wavelengths, and therefore they'll become efficient radiators and hence interfere with other circuits within the system. Okay. So skin effect and radiation also increases with the effective resistance of the conventional wires, and therefore in such cases we can have only resonators that have a given Q, okay, with lumped elements. That is, if we were to make an LC tank circuit, we expect that its impedance at resonance is infinite, but it's rarely infinite because the coil will have a coil resistance, the capacitor may have a shunt conductance as well, and this will add up and will have a residual impedance. It could be high, right, but not infinite as expected. So we look at rectangular cavity as shown below. That is, we have a box, okay, we started with our waveguide with a height of B and a width of A, and we cut it off at a given length in the Z direction. And then somewhere along the way, we have cut a hole and put in a probe. This could be a coaxial line that is open is cut off, then we strip back, okay, the jacket and let the inner conductor probe out. This becomes an efficient antenna. That's the only way we can connect in. We can launch a wave inside a waveguide. We must use an antenna to launch it, to launch the signal inside. So this is being used as a launcher, and the variation of it is to use a loop, a current loop. Therefore, we'll be using the magnetic field to radiate the signal into the cavity. So that's how it looks. So in the Z direction, we have a length of D, the height is B, and the cross section is A. So we choose the Z axis as the reference direction of propagation, but because of the conducting termination at Z equal to 0 and D, only a standing wave pattern will exist inside the cavity. And then we must use 3 indices, which we choose to be MN, coming from our usual waveguide terminology, and P to denote the TM or the TE standing wave pattern inside the cavity. So in a rectangular waveguide, we assumed that the axial variation of the field has the exponent of minus j beta z for a mode that was propagating in the positive z direction. And the wave will be deflected back at the termination and propagate back in the minus z direction with a propagation factor exponent of j beta z on reaching the termination at z equal to d. And we consider the EY component of the electric field for the TM mode, whose boundary conditions at Z equal to 0 and D require that EY go to 0. And this implies that EY must vary with Z as sine beta Z, where beta is just going to be given by pi d by d, where p is an integer and must hold true for the EX as well. And since the factor minus j beta appears due to the derivative with respect to z in the component of the del operator, the other components must have the cosine of beta z variation whenever this factor is missing. And thus, for the TM and MNP modes, we then have the components having that kind of weird kind of mathematical value, where kc squared is defined as m pi by a squared plus n pi by b squared, just like in the normal waveguide. The others are just applying the values of p. So for the TMNP modes, the resonance frequency of the cavity will therefore be given by omega MNP equal to c, the square root of that values, and we see that this is going to be given by 2 pi FMNP, and the transverse electric field components must then vanish at Z equal to 0 and D as well, while EZ is equal to 0. That is for the TE modes. Thus, the Z variation will require a sine P pi by Z of D, and the factor JB appears there as well, and therefore all the factors, without the factors, must be multiplied by a factor of minus P pi by D all through. And thus for TE modes, we have again that kind of expressions which I'm not going to go through, and we note that FM and P is the same as for the TM and P modes. So hence, the modes, all the modes in the rectangular cavity are going to be degenerate as long as none of the M, N, R, or P is 0. And the mode with the lowest resonance frequency will be the dominant mode in that particular cavity. And for the TM modes, the axial and transverse electric field components will be in time phase, but in quadrature phase with the magnetic field components. And hence, when we take the time average pointing vector in any direction in the cavity, it's going to be equal to 0. And for the TE101 mode, in an A by B by D cavity, the only non-zero components are therefore just going to be reduced to that value there. We just have an HX, an HZ, an HX, and an EY. Okay, and this may be excited by inserting a probe in the cavity region at the top or the bottom faces where the EY is going to be maximum, or by inserting a current loop to couple the maximum EX inside the front or the back faces. So the best position for the probe or the loop will be affected by the impedance matching requirements of the microwave circuit where you are going to use the cavity. And a common method of decoupling of energy out of the cavity is again by introducing a small hole or an iris at an appropriate location in the cavity wall. And the field at the hole must have a component that is favorable for exciting the desired modes in that cavity. So, example 5. Determine the dominant modes and their frequencies in an air-filled rectangular cavity resonator for A greater than B greater than D, and for A greater than D greater than B, and for A equal to B equal to D, where A, B, and D are the X, Y, and Z directed dimensions of the cavity respectively. So with the Z-axis chosen as the reference direction of propagation, then neither M or N can be 0 for TM modes, but TE modes will allow either M or N to be 0, but not simultaneously. P cannot be equal to 0 because of the sign variation of the E or in the Z direction. And thus, the lowest order modes will be the TM110, TE011, and TE101, with TM110 having the lowest resonance frequency for A greater than B greater than D, and given by that value there. The T101 mode will have the lowest resonance frequency for A greater than D greater than B, and given by that equation. And while all the other three modes will have the same resonance frequency for A equal to B equal to D, and will have a value of that value there. So the walls of a practical cavity with finite conductivity, and hence the walls of a practical cavity have finite conductivity, and therefore will have ohmic losses in them, especially as the field penetrates into the guide walls. And we define a quality factor of the cavity as twice pi multiplied by the time average energy stored at resonance divided by the energy dissipated in one period of the at resonance. And we let U be the time average energy stored in the cavity, and we write then U is going to be given by the sum of the energy stored in the electric field and the energy stored in the magnetic field. So if PL is the time average power dissipated in the cavity over one period, then the dissipated energy is going to be given by PL divided by omega, so that we can get that Q is going to be given by omega mu or U over PL. And in determining Q at resonance, the loss will be customarily assumed to be low, so that the field patterns are essentially the same as in a lossless case. And for an A by B by D cavity, and carrying the TE101 mode, the time average stored energy is going to be given by that value for the electric field, and where Kc is of course pi squared by A squared, and the magnetic field will have a current that is given by that value. Look at the volume of the cavity. And since F101 has that variation, then you can see that U of M is equal to U of E, and U is therefore 2 U of E, and we get a value of 8 mu naught by 8 multiplied by the volume of the cavity into 1 plus A by D all squared, and multiplied by the magnitude of the electric field. So to compute the power loss, we note that the power loss per unit area is going to be given by the average of that pointing value, that is the surface current density on the wall, multiplied by the resistance per square, and we get a value of 1 by 2 the modulus of Hg squared by Rm. And therefore, power loss in the back wall will be the same as that in the front wall, so that PL is going to be given by the integral over the surface, and we get a value for that is in the back wall, okay, and in the opposite walls, then we have to get that one for the others, that is at z equal to 0 and so forth, and we get a value of that case there. So we have 4 walls, that is with 4 walls of 6. Yeah, we have 6 walls, so to speak. And hence, Q will have that kind of expression where we have the volume of the cavity. So what would be the size of a hollow cubic cavity made of copper in order for it to have a dominant mode resonant frequency of 10 gigahertz? And then proceed to determine the Q of the resonator at this frequency. And we have here that F of 101 is going to be given by 30. That is the speed of light divided by the cutoff frequency. That is √8 centimeter, and we get a value of 10 gigahertz, and therefore it tells us A is going to be given by twice 21.2 millimeters, and the Q will be given a value of 10,700 with a copper walls of having conductivity of 5.8 times 10 raised to 7 Siemens per meter. And we see that for the cavity, we have a very high Q, okay, compared to an RLC circuit that you'd be able to make in any given circuit that you'll be using. And at microwave frequencies, there is no lumped element resonator that would give you that kind of Q. So that brings us to the end of that. And I think I'm at 10:21. I can take a few questions, then we can take a 5-minute break. So any question? Let me just ascertain I'm not alone in class.
There's some few questions in the chat.
Let's see. Now, this one you're asking for students on the line. Who are these ones waiting? I don't see any. Then, now the only question there is about what kind of signals or waves are produced at base station antennas. Odipo, just give me a guess. What was the nearest guess? Mr. Odipo? Is Mr. Odipo in class?
I think Mr. Odipo is not in class.
So how did he ask the question and disappear? So who am I going to answer? Can you give a guess of what you would expect the signal to be like? So the antennas usually, say for example, depending on how you are looking at them, what we have is that an antenna being a very small kind of device or structure, we can assume that the waves leaving the antenna at that particular time would be spherical TEM waves. That is, they are almost like plane waves, but since we are nearer the source, they'll be radiating out in a spherical kind of space. Okay? It's like coming from a point and being radiated out. Now, the base stations, usually what happens is that they are radiating, say for example, there are those ones which have reflectors to try and point the signal in one direction. But by the time they arrive at your phone, you are so far away that the signal will be almost a plane wave. Okay? So that's how it's being sent to you wirelessly by propagating through air. And then the antenna in your cell phone captures that signal or part of the field, which excites and which is converted to an electrical current, and this is then amplified by the amplifiers you have in your phone. Okay. Yeah, there's a guy who says, of course, yeah, they are radio signals, of course, but the question was what kind of waves. So mainly we can say that when they leave the antenna, they will be in the form of TEM waves that are spherical, that is, they are radiating in all directions, especially if we don't have a reflector. And then as they get near to your phone, we are very far away from the source, and therefore the wave will be almost like a plane wave, because in any case, the antenna in your phone is so small that it can only pick a very short section or a very short part of that wave front. So it will appear to it for all practical purposes as a plane wave. But they are all TEM waves. Remember, as long as you are not guiding the wave cannot be TE or TM. If it's propagating in free air or in free space, you have no problem with those waveguide modes do not propagate. The TE and TM come because we are confining the wave to propagate in a confined area, so to speak. I hope I've answered that. So whoever has understood can always appraise Mr. Odipo who left us. So any other question, or if there is none, then I will meet at 10:35. I get me a slug of water.
Okay.
Okay, in 5 minutes then. So we can continue now. And now that we have looked at the rectangular waveguides, we have seen the cavities that we can form with the waveguides. But if you look at the kind of mathematics, usually what you are expected to know most of the time is where we have only single mode operation, and usually the equations that, or the form of the modes or the number of modes that you'll be having will have very simple kind of variations. So all you are expected to know is the concepts of cutoff frequency. Note that the cutoff frequency is not a frequency related thing like you get in a RLC circuit, but it's formed, the cutoff frequency is because of the geometry of your guiding structure. So, and the usual way of it cuts off is by reflecting away the waves that are going in, and therefore we can use a waveguide as also as a form of a filter, so to speak. So now we want to look at what we call the circular wave or section waveguides. These are of historical importance, and also in areas where we have things that will be turning, you'll find that it's easier to turn something that has a circular cross-section rather than having corners. And most of the time is when you are feeding, say, an antenna and so forth. So, with circular section waveguides, the diameters usually in the practice usually range from about 63.957 to 0.607 centimeters to cover the 800 megahertz to 116 gigahertz range of frequencies. They are mainly found in measurement systems and radar systems. But the guides are less common, except when we have rotary junctions. So we consider a circular pipe. This could be like a water pipe that we use in the house. So it's a round pipe, okay, with conducting walls as shown below, where we have a diameter from the center to a radius of A, and the pipe wall has a finite thickness. But for us, for now, if we assume that the pipe or the walls are perfectly conducting, the thickness is of no consequence, because then spin effect is not an issue, because the depth of penetration would be zero in that particular case. But in terms of calculating the attenuation constant, we shall require to know what the thickness would be to ascertain that it's much thicker than a spin depth at the operating frequency. So we'll decompose the Laplacian, that is the del operator, has now to be decomposed into axial and transverse components, but we shall use cylindrical coordinate systems because, as we have seen the cross-section of that pipe, we have cylindrical symmetry or circular symmetry around the pipe walls. So in a charge-free region of the dielectric inside the waveguide, then we can see that Ez for Tm modes is going to be a solution of the Helmholtz equation given by del T square of Ez R of phi and phi plus Kc squared of Ez R and phi equal to 0 for Tm modes, and for Te modes, the Hz will be the solution of the similar equation, but now using the magnetic, the axiomagnetic field component. So we'll express the equations in the cylindrical coordinate system as follows. The Laplacian, that is del T, has this value Usually you are not required to remember this. Many of the times it will be given at the back of the paper or in a book. You don't have to derive the coordinate systems. So this is how the circular cylindrical coordinate system will look like for the Helmholtz equation for the TM modes, and for the TE modes it will have that kind of value, and Kc will be gamma squared plus omega squared mu epsilon, where this is the K value that we got for the medium between the pipes or inside the pipe, okay, for the free medium, so to speak. So we propose that Ez for the TM modes, that Ez can be expressed as a product of two analytic wave one-dimensional functions as Ez of R of phi equal to RR multiplied by phi of phi, where phi of phi will be called the angular or the angle expression or angle equation or function, and R of R will be the radial function. Thus, when we apply this equation in the Helmholtz equation, we see that that equation separates into two components, one corresponding only to the radial function, and the other side corresponding only to the angle function. And since the radial function or the radial equation is equal to the angular equation, then the only reason this can happen for all R and phi is if each side of the equation is equal to a constant. And the constant should be the same. So we let V or nu not equal to 0 be that constant such that we can write that 1 of phi d2 phi by d phi squared is equal to minus V squared. And we notice that this one is a simple harmonic equation with sinusoid or cosine function, okay? And then the radial function can then be written as R of R by R of R dr R dr dr plus that is going to be equal to V squared, because it was equal to the minus of 1 of phi. And therefore we can see that this can be expressed in this form, that is, we take the values to the other side and we get a value of R squared minus V nu by R all squared, and R of R equal to 0, where we have opened up this bracket here. And this is called a standard Bessel differential equation. So that is, the radial equation is a Bessel's differential equation. Now, for the TM modes, we have that Ez of R phi and Z equal to Ez of R multiplied by the exponent of minus gamma Z, where Ez of R of phi is equal to that. And since all field components are periodic in phi with a period of twice pi, then the only admissible solution would be either sine n of phi or the cosine of n of phi, or a linear combination of this in the expression for phi of phi. But what we'll notice is that sine n of phi and cos n of phi are only different with respect to the reference or the point we choose to be a reference. That is, there is only 90 degrees difference between cosine and sine. And therefore, you can just use one of them and ignore the other, okay? Because where on the pipe wall are we going to call the reference? We can choose that one arbitrarily. So we may choose either, since this only results in a shift in the choice of the phi equal to 0 reference point. And if we let Ez of R of phi equal to Jn Kcr, where Jn Kcr is a solution of the radial equation, then we'll multiply that one by the cosine of n phi, and then we'll see that Et is equal to the R component plus the phi component, and this must be equal to the minus gamma by Kc squared, the gradient of E of Z from the reduced Maxwell's equations, where the transverse gradient of E of Z will be given in terms of the cylindrical coordinates by that equation. And thus, we can write what E of t is going to be. So I'm using the Jn prime to represent the derivative with respect to r, okay, for that function. So for the other one, of course, it's easy. We can always, the derivative with respect to phi is easy. We just can put that one in. And therefore, the transverse electric field will be given by that equation there, and the magnetic field components will be given by that particular equation down there, where Jn prime of Kc is equal to that. Remember, Jn of Kcr is a solution to this equation that we have here. That is a solution of this equation, okay? And is called a Bessel function of the first kind. Now, Ez must vanish at r equal to a, and hence we must choose Kc multiplied by a, that is Kc multiplied by r at r equal to a, such that it corresponds to the zeros of the Jn of Kc of a. And if the nth root of Jn Kc of a is equal to 0 is Pmn, then the allowed eigenvalues for Kc are then going to be given by Kc equal to Pmn divided by a. And the choice of m and n will then specify the particular Tmn mode propagating in the guide. M is usually the number of circumferential half lambda variation of the field. That is how many wavelengths we have along the circumference in the phi direction. The n is usually the number of lambda by 2 variations of the field along the radius. That's how many times how many sine waves or sinusoidal waves or cycles can we fit between the center and the circumference, or the wall of the guide, where the tangential E field must go to 0. So for the Mn propagating mode, the propagation coefficient is going to be given by beta Mn equal to the square root of omega squared mu epsilon minus Pmn by a all squared. And the cutoff frequency is therefore going to be given by twice pi a by Pmn. So the wave impedance will be given, of course, by the ratio of the transverse electric field and the corresponding transverse magnetic field component. Remember, ER corresponds to the H phi, and E phi goes together with the HR. And therefore, we see that ER by H phi must be equal to the minus of E phi by HR, and this is given by beta Mn by omega epsilon. And this can be written as the intrinsic impedance of the free medium multiplied by the velocity of light in that medium and multiplied by beta Mn, or the propagation constant. So the first few zeros for J and Kc of A are shown below, and we have that for n equal to 0, we have for P1n or P10 we have 2.405, P20 we have 5.520, and so forth. For P11 we have 3.8, and so forth. And since we have seen here what the cutoff frequencies are, the cutoff frequencies, the wavelengths, we can see we are dividing by Pn. You can see that in this particular case, the P10 mode, okay, will be having the biggest or the largest wavelength, and therefore the lowest frequency. So for the TM01 mode, Kca is equal to that, so that we have a Kc equal to 2.405 by A, and the M field of or about 0.383 C by A. So for this mode, only the EZ, ER, and H phi will be non-zero, and the TM01 in the circular section waveguides will be analogous to the TM11 mode in a circular or a rectangular waveguide. And we note that TM0N or TM0 modes do not exist in rectangular waveguides anyway, however. So the electric and magnetic field lines for the TM01 mode in a circular waveguide are then illustrated as shown. That is, the E field is radial, okay, everywhere radial to the guide, and the magnetic field is circumferential. For TE modes, now the solution we'll be looking for is that one of HZ, okay, and it should be a solution to that Helmholtz equation there. And we can write this as a value of Cn, Jn, Kc are cos n pi n phi, because the equations will be similar, only that we are using a different value of a different field. And therefore, we can see that the transverse magnetic field component will be given by that expression when we use the Maxwell's equations, and the transverse electric field will be given by that equation there. So we require that the radial derivative of h of z, or the normal derivative on the surface, vanish at r equal to a, and therefore we must have that hz be given by b1 cos n pi of that, with ddr jnk c of r equal to jn prime or kca equal to 0 at that level. So if the roots of this equation are given as p prime, then we can see that Kc is going to be given by p mn prime over a, and the first few roots for that derivative function are going to be given as shown, with m equal to 0, 1, 2. We have pm1 equal to that value there, pm2 equal to that value, and so forth. And here we see as another thing, that this will have the shortest wavelength, so to speak, the longest wavelength, so to speak, in that particular equation. So we see that TE0N and TM1N are going to be degenerate because the properties of the base of functions is such that the derivative of the 0th order base of function will have a value of the minus of the first the first order base of function. Rather, that P0n prime is the same as P1n. Okay, the zeros, that is, of the two functions will be related in that form. So the first propagating TE mode is the TE11 mode, with a lambda c given by twice pi a over 1 p over p prime 1 1, which is given to 2 pi by 1.841 a, and we get a value of 3.41 a there. For the TE0n modes, the attenuation constant is given by alpha equal to Rm over Az naught over Fc squared by F into that equation there. And this will decrease as F raised to 3 by 2 at high frequencies, because Rm also increases as the square root of F. And therefore, this property is a unique property for TE0n modes in circular waveguides, and it makes it possible to make very long, low-loss waveguide communication links. The problem is that for the TE0n modes to propagate, other modes will be propagating, and therefore it's usually very difficult to have those other modes propagating, so to speak. That is single mode operation of the guide. Okay. Any small irregularities in the guide walls will lead to power leakage from one mode to another, and therefore this can have two serious consequences. One is loss of power from the desired TE01 mode, and the conversion of power back and forth between the desired T01 modes and the other modes, and this can result in serious signal distortion because of the difference in the dispersion, because of the dispersion occasioned by the different modal phase velocities. And at the same time, at the end where you are siphoning off the power or you are tapping off the power, you'll have terminated the line for a given mode alone, not all of the modes. And therefore, the power in the other modes will just go wasted. So currents associated with TE0N modes are in the circumferential direction only, and this property makes it possible to construct mode filters that will suppress modes with substantial axial currents. So how you can make this is to use a small pitch helical guide, okay, where you have a coil that is tightly wound, that is almost like a solenoid, so to speak, with the coils vanished from each other, that is insulated from each other. And the small pitch means that the coils form almost a circular kind of variation along the guide, although we know that it's not really completely circular. But because of the pitch being very small, we can approximate it with a circular value. And therefore, the current will just be seen to be flowing only circumferentially, and none of the current will be flowing along the axis of that guide. So the attenuation constant due to a finite conductivity of the guide wall may be determined in the same way as in the rectangular waveguide. And the attenuation constant for the TE0N modes decreases monotonically with the increasing frequency. Remember, because we are going to deal with integrals of the base of functions, the mathematics now is no longer that simple as in the rectangular waveguide. Okay? And usually we don't usually test whether you can do mathematics. We just want to see whether you understand the principles behind the waveguiding properties of structures. Example 1. A 10 gigahertz signal is to be transmitted inside a hollow circular conducting pipe. Determine the inside diameter of the pipe such that its lowest cutoff frequency is 20% below this signal frequency. If the pipe is to operate at 15 gigahertz, what would be the waveguide modes that can propagate inside the pipe? So we have that FC of TE11 is going to be given by 0.293C over A, which is equal to 0.0879 of 8 gigahertz and about a value of 8 gigahertz there. And the 2A is of course 2.2 centimeters. The inner radius of the pipe is therefore going to be given by half of that, which is A, and you get a value of 1.1 centimeter. And thus, FCTM01 will have a value of FCTE11, which has a value of that. We get 10.45 gigahertz, where P and P prime are the zeros of the JNKC and the JN prime KCA respectively. And therefore, for the TE21, we have 13.27 gigahertz. All the other modes okay, will have FCs greater than 15 gigahertz and therefore will not be propagating inside that pipe. Okay. Example 2. Find the cutoff frequency of the first two propagating modes of a circular waveguide with A equal to 0.5 centimeters and epsilon r equal to 2.25. If the waveguide is silver plated and the tangent, the loss tangent is 0.001, calculate the attenuation in dB for a 50 centimeter length of guide operated at 13 gigahertz. So TE11 and TM01 are the first propagating modes, and therefore we can say that for the TE11 has a cutoff frequency of 11.72 gigahertz. The second, the TM01 has a guide gigahertz, 15.3 gigahertz, and since we are operating at 13 gigahertz, then only the TE11 mode will propagate inside that pipe, and therefore the pipe is being operated single mode. And thus, the K is going to be given by that value there, which is about 4.08 times 10 radians per meter, if you like, but you can always convert that and divide that by twice by pi, if you like, to get in terms of multiples of pi. So for the TE11 mode, The beta is going to be given by 176.7 per meter. And the attenuation due to the dielectric is alpha D going to be given by K squared by cos beta tan delta, which is given by 0.47 nepers per meter. And the Ag or the silver conductivity is given as 6.17 times 10 raised to 7 Siemens per meter. And this gives us a value of, correspond to a value of 0.29 ohms. And that's the attenuation due to the conductor is going to be given by alpha C equal to Rm AK multiplied by that value there, and you get a value of 0.066 nepers per meter. We see that the dielectric loss will be dominant in that pipe, and the total attenuation is therefore going to be given by alpha C plus alpha D, which is about 0.547 nepers per meter, and or the loss is going to be given by the 2.38 dB, that is given by the minus 20 log that value there. So the properties for the circular waveguides, just like we did for the other case, we just show the expressions. The expressions will have that kind of weird looking, and for the H modes, we'll have that kind of values. And for the TE modes, TM modes, again, we have that expression. And for the TM modes continued, we have that. And we note that for these modes, the Rm is just going to be given by the square root of omega mu naught by 2 twice sigma. The conductance or the admittance Y naught, characteristic admittance, is going to be given by 1 over Z naught, where Z naught is equal to root mu naught by epsilon naught. And epsilon 0, 1, this is the Neumann factors, will have that kind of value. So now, because the coaxial line is a circular section kind of guide or transmission line, only that we have a center conductor, the coaxial line can support TE and TM modes when the frequency is high enough. And usually the bandwidth, the highest frequency in which you can operate the coaxial line single mode, is when the first waveguide mode starts to propagate. So in many cases, for at the usual frequencies of operation of a coaxial line, the TE and TM modes are usually evanescent because their cutoff frequencies are way above the operating frequency. So the dominant waveguide mode in the coaxial line sets the highest frequency limit of the line itself. And hence, the dominant TE11 mode in a coaxial line has a special interest because it allows us to design our circuits or our coaxial line communication links. So since the region of interest A less than R less than B does not include the origin, the solution of the radio equation will also must have another solution that is different from the first one. This Neumann function is usually indeterminate at the center. That is, it blows up to infinity at the center. We shall show this when we look at how we can solve that problem, the base of function solution. And therefore, the axiomagnetic field intensity will be given by the azimuthal angle or the angular solution multiplied by a component that varies as a base of function of the first kind and another component with a Neumann function as the solution. This Neumann function in the literature, especially in the English-speaking countries, is usually referred to as the base of function of the second kind. This will be base of function of the first kind, and that is base of function of the second kind. In the German area, this one is usually called the von Neumann function, okay, and that one will be called the base of function. So we require E phi of R phi be equal to 0, and since that is given by that value, then we must have that B1 of Jn prime Kca plus that is equal to 0, and the other one must be equal to 0 as well. That is B1 of J prime and case B and B2 Y prime KCB equal to 0. So we express this in matrix form as that, and we require that for B1 and B2 to be non-trivial, then the determinant of this 2 by 2 matrix must go to 0, and therefore we must have that Jn prime KCA multiplied by Y prime KCB equals to J prime N KCB equal to the Y prime KCA. And Kc will then define the cutoff frequencies of the TEMN modes in the coaxial line. For n equal to 1, Kc is approximately 2 by A plus B, and once Kc has been determined, the propagation coefficient or the cutoff frequency can then be calculated. The field distributions for the TE11 mode in a coaxial line therefore have the following variation. You see that the field is not entirely radial like we had in the circular pipe, but we have a soccer ball kind of variation. So example 3. A piece of RG142 coaxial cable has A equal to 0.035 inches and B equal to 0.116 inches. Remember, this is the radius of the center conductor or the inner conductor, and that's the inner radius of the outer conductor. And epsilon r, that is the dielectric between the conductors, is 2.2, has a dielectric constant of 2.2. So the question is, what is the highest frequency the coaxial line can be operated before the TE11 mode starts to propagate? Now, B by A is of course given by the ratio, and we get a value of 3.3, and we can use curves for KCA versus BA to obtain the value of KC. However, if we use the approximate solution that we got for KC, we can write that as KCA as given by 2 by 1 plus B by A, which is equal to 0.465. And thus, the FC11 is equal to CKC over twice pi root epsilon r, and you get a value of 17 gigahertz. So in practice, we need to allow a 5% safety margin in case of any problems we have in our line properties, that the cutoff frequency does not drop lower than this, than 17 gigahertz. And therefore, what we do is that we now use the highest frequency for which you can drive the line is about 95% of 17 gigahertz, and you get a value of 16 gigahertz. So for most coaxial lines, the connectors used in practice are constructed for characteristic impedances of 50 ohm, except for the 75 ohm line used in TV systems. This is just an industry standard. It's just what we have used, because in many cases, for TV, we are using antennas which are mainly voltage detectors. That is, we are just going to detect the electric field. So we'll convert that electric field into an voltage. And therefore, we want to make sure that we get as much voltage out of the antenna as possible. Now, many times you'll find that for any line, the maximum power handling capacity is when the Z0, that is the characteristic impedance of the line, is about 30 ohms. And therefore, and in microwaves, we are usually not interested in voltage or current, because in any case, they are very difficult to measure. All we can measure in microwave circuits is the impedance and the power. And therefore, we want to maximize that kind of, to compromise. And therefore, the 50 ohm can be seen to be a geometric average of 77 ohms for the maximum voltage before breakdown, and the 30 ohm maximum power handling capacity of the line, and you take the square root, it will be around 50 ohms. So this 50 ohm and 75 ohm are chosen by the industry. It's an industry standard, so to speak. It doesn't mean that you can't have lines with higher impedances and so forth. This is informed in the TV, this is informed by the radiation impedance of the antenna that is usually connected to the TV. Many times if you go to if you look at the, say for example, a dipole, like the one in a police station, the dipole has about an impedance, a radiation resistance of about 73 ohms, which is very close, and therefore the reflections will not be much when you connect it to a line that is connected to the TV system. So the rationale behind this is that the attenuation of an air-filled coaxial line is minimum for a characteristic impedance of 77 ohms, while the maximum power handling capacity will peak at about 30 ohms. And therefore, the 50 ohm characteristic impedance is roughly the geometric mean of the two impedances, and hence a compromise between power handling capacity and the attenuation. So for power handling capacity, high power handling capacity is usually more important for microwave systems because the powers that we'll usually encounter there are usually very large. And for TV systems, the signals from the antenna are small, and the power handling capacity is not really of priority at this particular case. And the connectors are then used in pairs and must possess certain characteristics, such as one, they have to, once we connect them, they must have very low standing wave ratios. They must cause very low standing wave ratios. That is, the reflection coefficients there must be low. Two, any higher order mode free operation at high frequencies. That is, we want to have as wide a bandwidth as possible before the next higher mode starts to propagate. And high repeatability, because the connector will be connected and disconnected as we connect the stuff onto the measurement equipment or into the system, then we must be able to ensure that the characteristic of that connector, when it has been connected to the system, is the same all the time we do this, we go through that process. The mechanical strength must be high because of this, they are handled all the time. And therefore the types that we can get are usually first, we got what we call the type N coaxial connector, named after the person who developed it, called P. Nail in 1942. And this will come, the connectors, we say they come in pairs. We can have a male and a female connector, and they must be threaded together. So the female has an outer diameter of approximately 0.625 inches, and hence the connector operates up to about 11 to 18 gigahertz with a standing wave ratio of around 1.07, which is very small indeed. The SMA is called the small sub-miniature, okay? The sub-miniature type A adapter, developed in the early 1960s. This fabrication is motivated by the requirement for light and compact connectors. These are the ones you are most likely to encounter when you start doing fifth year. Yes?
Yeah. Your time is running up.
Oh, it's running up. So then I'll stop there then, and we can continue with the connectors next time. Okay. This one will be given, it's given as to complete the case, because then you are going to encounter them, especially when you start dealing with design, especially for the fifth year projects and the likes. Okay. So any other question? Do we have any questions before we break? No question apart from telling me my time is up. So in case there are no questions, then I'll then wish you a nice weekend. Yeah, let's meet on Wednesday, God willing.
Thank you.
Hello, sir.